Hello and welcome to the Siemens Digital Industry Software webinar. My name is Matthew and I will be your IEEE Global Spec moderator, and I want to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface. The large window with the heading Presentation in the upper left is the primary window for today's webinar. Just to the right of the main presentation window is the speaker bio window with background information on today's presenter. Just below that is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will be placed in the queue to address when we get to the Q&A session. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. Now I would like to introduce today's presenter, Jay Garagia. Jay is the Director of Global Digital Manufacturing Services at Siemens Digital Industry Software. He has 27 years of experience in electronics design and manufacturing and multi-domain manufacturing processes. Currently managing a consulting organization with responsibility including strategic and financial planning, go-to-market strategy definition, and business development. Mr. Garagia works with design and manufacturing organizations to help them realize their digital manufacturing and digitalization strategy. He has worked with hundreds of design and manufacturing organizations around the world, resulting in real improvements through a systematic, metrics-based methodology. Mr. Garagia holds a bachelor's degree in electronic engineering and an MBA in technology management. He has published a number of articles and white papers in industry-leading technical magazines and industry conferences. In addition, he is a regular keynote speaker, as well as a regular speaker at regional and international design and manufacturing conferences. Jay, welcome to today's event, and with that I will pass things along to you to get started.
Thanks, Matt, for the introductions, and thank you everyone for joining this webinar. Over the next 45 minutes or so, I'll be going over how we at Siemens help clients improve throughput with their systems assembly and work cells at electronics manufacturing factories, and how to do it safely. And we'll also review some case studies at a PCB assembly factory. Starting at high-level business challenges, most organizations are running various different levels of production. Many of them are dealing with productions that need to be driven on the same line as variants come in and more products come in as the number of projects grow. And hopefully that trend continues as we work our way out of this current climate we're in. And there's a lot of push to global production. The risks now of being able to build the same way we used to build and ship things around as easily as we used to just isn't quite there with the current geopolitical climates that we have. So there's challenges involved with that around not only shipping, but also component acquisition and supply chain readability. So in all, planning and production is being challenged. We're dealing with more with the same assets, more projects, more products, more variants, and more uncertainty at this time as we work our way out of the current climate and into restarting manufacturing, at least in the US here, as we look to the next few months. One of the ways organizations have been meeting challenges that we described earlier is by going digital. And when I mean digital, I mean digitalization of factories. What we see here is a PwC research for over several hundred organizations earlier this year, in which many of them are investing in creating digital factories. You can see the statistic there of 91% of them responded that way. And 90% of them also responded believing that the digitalization of factories will offer more opportunities than the perceived risks that exist today. All in all, I think the main goal here of digitalization and creating digital factories is to drive efficiencies. We're trying to get ourselves back into a situation where we can increase efficiency, improve our bottom line, and work towards improving the overall health of factories here in the US. With all that being said, we do have to focus on the now as well. We do have to get our factories going again and decide on what that next normal will be. And that's where a research by McKinsey and Company comes into play. They published a paper specifically around this topic, and they cite three main areas of focus to respond and get back to the next normal. The first one is to protect the workforce, which seems obvious, but I'm not sure many organizations have formalized operating procedures and processes that hover around this new next normal, this discussion about distancing and temperatures and everything related to that. We need to, of course, ensure business continuity, but this could have potential impacts on how we model the way we work in the plant, and more importantly, how we interact with our customers and our suppliers in different ways. And finally, how do we drive productivity and potentially at a distance? There may be a percentage of companies that have decided some work may be done remotely. Okay, so what does that mean, and how can we put policies in place that will support that, both infrastructure point of view as well as being able to do it effectively? And then in the plant itself, how do we maintain and ensure that productivity is maintained while also addressing social distancing and various other aspects of this new next normal? So we talked about digitalization, we talked about how we need to consider the now, and there's a lot of systems and a drive to automate in the process in order to drive efficiencies. But let's take stock at where we are. Technologists and software organizations and even the machine vendors have been talking about smart and Industry 4.0 for many, many years. And I believe that we've done a really good job of setting a strong foundation for connectivity, for example, where most equipment out there, SMT equipment, testers, conveyance, they all have the ability to connect. We've got standards out there, whether it's the new ODB++ standard for machine connectivity and machine-to-machine connectivity, whether it's the IPC standards, the Hermes standard. There's so many out there now that enable connectivity and allow us to not only communicate machine to machine, but better communicate to software and optimize that. Speaking of optimization, machine vendors have also accelerated their ability to optimize their equipment to a degree that's really brought our productivity forward. A lot of the equipment and the software vendors provide simulation. So whether it's inline simulation, programming simulation, or even offline simulation, we kind of know what we're going to get with a lot of this equipment. And then finally, there's been a lot of analysis tools out there that allow manufacturing organizations to better utilize their factory, their assets, their equipment, and optimize throughput through these automated production systems. One aspect of automation that's been creeping into many factories is the introduction of collaborative robots, or what's commonly known as cobots. More and more organizations are implementing them. And one of the main reasons, amongst others, that seems to drive the need for them is based on this Deloitte study in 2018, where there is a skills gap that's impending, according to the study. At the end of the day, by the year 2028, most likely there'll be 2.4 million open positions. And how do we fill those positions? And Universal Robot's perspective, a cobot may be a good alternative to trying to fill those positions and keep production levels at what they need to be. Another interesting data point related to cobots is a research study by MIT Research in which they cite an 85% increase of productivity if humans and robots work together rather than individually. I don't think there's any surprise here as the trend of more customization and higher number of variants. Programming robots has become easier, but there's nobody as agile as a human. So it seems as though what's intuitive to us with humans and robots working together is statistically also expected to be the better way to go. A lot of the automation that I've been speaking about in terms of connectivity, optimization, simulation has heavily been focused on automated equipment, whether it's SMT equipment or various testers and conveyance and so on. But what happens after this process is done? This is when we get into what I'm calling the last mile. These are those processes that are manual, whether it's manual insertion, semi-automated processes using cobots or not, and even system assembly, box build, cells. At this point, everything is manual. So everything we spoke about in terms of connectivity, optimization, simulation, comes to a grinding halt. Well, perhaps it's not a grinding halt in every organization, but for most organizations, they not necessarily have the capability to optimize and simulate all those manual processes, but rather use experience and tribal knowledge to try to do the best that they can to get the outcome of throughput. So there are a lot of throughput cost and risks associated with the manual and semi-automated processes as well. How can we systematically optimize throughput, and how can we do that safely? Let's take a look at that in the next section. So given the pressures of new product introduction frequency and what we talked about earlier in terms of trying to do more with existing assets and different existing stations and cells, how do we improve throughput? And how are other industries doing it? And can we learn something from them? And one industry that we can look to is the automotive industry. Every 18 months, some automobile factory has to retool the lines in order to make way for a new model. And that new model may have new body styles, all kinds of changes when it comes to the insides of the automotive powertrain or parts of the engine and so on. And so there's this constant evolution of retooling, setting up, validating, and then doing the NPI, obviously, and then going into production. And they have to do this literally every 18 months as the models progress. So can we learn something from them and leverage some of that in the electronics industry? And we find that many of them go through this analysis of, okay, from what I have today, can I add extra stations here or there in order to improve throughput? Or would it help me if I added a couple of more resources in this area or an extra shift? Or various other questions around material access and routing the material to specific areas, and also ergonometric issues such as, is the safety of what the current procedures considered good for throughput? Are we slowing them down? Is there a better way to do that? And so on. And the consensus is that most automotive companies today use what's called manufacturing simulation. Part of that whole digitalization of the factory, they simulate in order to do the what if analysis and try to answer a lot of these questions. And it'd be great if we could maybe leverage some of that in order to optimize what we do in the electronics manufacturing industry. At Siemens, we have solutions across the full design through manufacturing product realization process, from the virtual product, developing the virtual product through our design tools, through production planning, manufacturing planning, building and managing the bill of materials, through production and production execution systems, and even out through integration to supply chain and service lifecycle management systems. However, as we work through pulling insights from these areas in order to optimize product development and driving continuous improvement through the process, for this particular presentation, we're going to kind of hone in on just the manufacturing planning piece and how do we optimize production for throughput with tools that we may have focused on the electronics manufacturing industry. We mentioned earlier that system assembly can be optimized, and we can do what-if analysis using simulation. So how do we do that? And what would it take to do simulation for a work cell and system assembly area? Well, we know that there's two constituents, two resources per se in these areas. One's a human. And normally for human simulation, we need some software that can not only analyze the spatial constraints around the area for where a resource such as a human would work, but also more importantly, the sequence in which they would work. And if there's any risks into safety or ergonometric issues or maybe material shortages because of the sequencing and so on, we can do a lot of what-if analysis if we have a simulation engine, like what I'm showing here today, that can consider a lot of that. The second constituent is a robot. Whether it's a robot standalone that's doing work maybe either in a hazardous environment or considered to be part of a work cell from maybe a customer, we can simulate that as well. And that's also critical to do, because not only should we validate the sequencing and also validate spatial issues there and potentially any ways to optimize throughput, but with the software that allows us to offline simulate it and then push an optimal program onto the robot remotely, we can also enable a lot of the things that we're considering right now, which is, robots working in proximity to humans, and are we going to be safe in doing so, and also enable some level of social distancing when it comes to spacing things out so you don't have potentially a manual operation or somebody delivering material too close to another person delivering material as the sequencing may require. And all that can be simulated, as we can see here. As I mentioned earlier, the use of cobots and robots working side by side may be quite effective. Programming new generation of these universal robots have also become close to drag and drop, as shown in this video. This allows factories to do what-if analysis in the areas of material flow and simulate delivery systems, identify bottlenecks, even monitor productivity levels and resources. A discrete event analysis based solution is probably the best way of simulating manufacturing environments such as this. In addition to simulating the specific robots or humans in the cell, we can also simulate the material delivery and the overall throughput of cells by running and optimizing material flow and running various what-if analysis on those cells as well. As we get business reopened and production started to ramp up again, the new normal, as we talked about earlier, may require additional factors. In this case, we model a work cell in which parts are picked from a designated location. Based on discrete event simulation, understanding the takt time of the stations and the sequencing of the operations, we model how many times the 6-foot radius would be violated and how to perhaps place shields or parts differently or even change the sequencing to be able to operate in a much safer environment. So we talked a lot about simulation, but how is it done? What is there a methodology behind creating simulations and making sure that they help us analyze throughput and the various different risks we talked about? And the answer is yes. At Siemens, we've instituted methodologies based on our understanding from other industries, and we've also defined that within the software so that new users can easily work in and start creating simulations in a systematic way. So we start by defining, obviously, what needs to be simulated, and we build process maps. VSMs, which are value stream maps, allow us to understand what the systems are, the inputs, outputs, queue times, and so on. And then shortly after we model that in the software, we collect data and validate that data. It's important that we collect real data for the area that we're going to simulate. So that way we have a learning set of data that we can then later use to also test and validate our model. We'll develop the model within the software, and the software has a tremendous amount of tools to be able to do this. Most equipment and human movements and those things are already built into the software. So a lot of it is drag and drop. And then we test and validate the model. So we take our collected data, ensure that the validated model is getting the results that we expect within whatever tolerance we're happy with. We develop scenarios. These are the what ifs. We simulate, we analyze the results of that simulation, and we could develop additional scenarios, additional what ifs, and then we would conclude the study. And as we mentioned earlier, there's a lot of different types of simulation that can be done, whether it's a robot, equipment, humans, as I said earlier. And we could be modeling for different things as well. Not only the physical and spatial things, but also cycle times and throughput and also the kinematic modeling of the robot and ensuring that the right things are happening while we're sequencing and programming as well. So let's take a look at some of the case studies that we've done in order to see how simulations can be used in electronics manufacturing. For our studies on whether we can use some of these simulation tools for a live or real PCB assembly factory, we chose Siemens Numeric Control in China. I know that many have that perception that all factories in China are massive with hundreds of lines and thousands of machines, but we chose this one on purpose because it is more indicative of factories outside of China, especially in the West. It's got 6 SMT lines, about 15 system assembly cells, and was an ideal candidate for us to run this type of a case study. So we ran 3 different case studies at SNC. The first one is a wave soldering machine simulation. They have 5 wave soldering stations that are fed with 15 manual insertion lines. Their current planning model doesn't really account for peak loads and conveyor speeds and capacity variances based on work orders that come in. And the planners do the best they can based on their understanding of what the capacity and what the machines can do. So the manufacturing engineers wanted to use simulation to see if they can improve throughput. The next study is a simulation of material delivery. At SNC, they use something called a water spider position. It's a methodology from lean manufacturing. And the water spider refers to a person whose main job is to make sure that materials are supplied to where they're needed, The water spider's rounds are time sensitive, and timing should be part of their routing and standardization. So this might end up with too many empty rounds, or they may be delivering material at times that is not necessary. So synchronizing with the work orders and ensuring that the planned routes of pickup and drop off of materials timely was critical. And then finally, a UV coating automation simulation was done at SNC. So at SNC, they have a automated cell that's based on a vendor supplied cell. And we did some initial studies based on the layout that they've done, some Excel based time studies to try to optimize its utilization. Production planners have quantity requirements for each one of these various wave stations, and those production requirements, if not met, would starve other parts of the factory. So after collecting data and building the value stream map that you see here, the software ran the simulation and found that we were only getting 48,000 units when anticipated planned budget was 51,000. So this was way below their forecast. To ensure our simulation model was correct, we compared our simulation values against actual values over a period of time for each of the stations. And we find here that, for the most part, our simulation engine was pretty accurate. We can then now develop scenarios, or what-ifs, in the software and try different combinations, letting the simulation work through some of its calculation and build several strategies. And then using the various strategies to identify the best model to use. In this case here, the key here is to build a model that production planners can now use to create the best sequence and production plan to hit the forecasted schedules as work orders come in and volumes change. In the next study that we needed to model and simulate was the position of the water spider factory we discussed earlier. The water spider's rounds are time sensitive, and maybe in larger factories this position can be replaced with AGVs, but the idea here was to build the value stream map and model as close as possible the existing routing based on the work orders and the requirements for the work cells that needed the materials using the simulation engine. We actually performed 9 different experiments of routes, pickup, drop-off scenarios, and tried to simulate the total route times for this water spider position. In our case, experiment 6 ended up being the ideal solution. We put it to the test, put it into production, and found a 25% improvement. Again, the simulation model was proved out and is now usable for future changes in schedules, work orders, material requirements by the production planners. In our final study, we modeled an automated UV coating cell. This cell was designed by an external vendor with an automated loading arm, the robot, and human resources supplying the material to the cell. It closely resembles a semi-automated work cell. The robot takes a ready part from one of the 2 tables and inserts it into the sprayer machine. The vendor provided the model for the robot arm, so we implemented the model and imported the recipe from the vendor into the software directly so we can run our simulation study. The human movement modeling was also important, as there may be factors of wasted movement, and we want to optimize for efficiency and speed while ensuring the actions are done safely within the proximity of the moving arm in this case. When we simulated the various combination of movements and programs, the ideal program was then pushed into the robot software directly using our simulation software. And the new sequencing and human movement scenarios were implemented, including having to place and even replace some of the placement kits and the locations of them in order to optimize the overall throughput of this cell. As we can see here, SNC realized the benefits of 35% line performance and shorter commissioning time, mostly because we were able to not only simulate an ideal scenario, but then the resultant recipe push it directly into the robot arm. Through the course of this webinar, I'm hoping that we were able to show how simulation, which is used in other industries, can also be used in electronics manufacturing. More specifically, it can be used in the parts of the factory that just aren't heavily automated, where humans and cobots may coexist, especially around system assembly areas, manual placement, and some additional work cell examples. We saw that it could help us eliminate problems and detect those areas in which we have time-consuming operations. We can optimize throughput while ensuring that work cells, operators, and robots can work safely. And we can enable continuous improvement and efficiency by feeding real plant data production back into the simulation engine so that we establish simulation models for risk-based decision-making as we continue to optimize for new orders, change orders, and variants. I'd like to thank everyone for joining the webinar, and thank you for the opportunity to describe our experiences and how we potentially can help factories in those areas that aren't fully automated, the work cell environments, as well as system assembly stations. Hope to meet some of you soon, and stay safe out there. Thank you.
Thanks, Jay, for that great presentation. And thanks to all the audience members for sticking with us. We're now moving into the Q&A session. If you haven't already asked your question, you may do so now by entering it in the Q&A box to the right of the presentation window and clicking Submit. We'll try to get an answer to it before the close of the event. Okay, let's see what questions we have waiting for us. Okay, first question came in from the audience. It seems difficult to get human movement modeled. How does the software assist with making that easier? Jay?
Yeah, thanks. Actually, it's a good question. Normally when we're getting into an area like this and you don't have experience with it, it could be daunting. But within the software itself, at least the ones we're using, there's two main strategies that people use to model at least the human aspects of it. Obviously, there's the models that come out of the box, kind of a starter library with the software itself, and that you can use to model movements kind of iteratively and incrementally, and teach it what and how and where you want it to move, and maybe whether that includes any pivoting, reaching in terms of arm length, and so on. And that can take a little bit of time if you're not comfortable with that type of software. So a lot of third-party vendors created what we call motion tracking equipment. And you've probably seen this kind of stuff in movies, right, where you see somebody wearing a glove or a bodysuit, and it's got all those dots on it, and those dots are tracked and recorded and then can be digitized. We use something very similar to make life easier for us. There's a lot of vendors out there, and maybe after the session's over, we can send whomever that may be interested in it a list of those partners that we support. CyberGlove, for example, being one of them, MotionWorks another. And they have various equipment to allow us to digitize movement in a much more natural way. And just having a human put on a glove, they go through the motions once, we record those motions, digitize it, and then away we go. We have a model. And that's probably the most efficient way of having it done. And then once that model is built, then you can do whatever you want to with it from then on, whether you're simulating spatial areas or safety concerns or even modeling it as part of the simulation next to a cobot. And so great question, but I think I would approach that as if you're comfortable with software or you get really good at it, you can do it pretty quickly. If you're starting out and don't know where to begin to create initial models that you may not have already in the starter library, some of these partners like CyberGlove and MotionWorks provide a pretty nice way to get things going. Thanks,
Jay. That's some pretty cool and interesting stuff for sure. Okay, let's see what else we have coming in from the audience. Okay, next question. Is there a way to integrate actual manufacturing performance with the simulated performance to improve the simulation model?
Yes. So I mentioned earlier that a lot of the software that we have within Siemens covers the whole product realization flow from design through manufacturing. And on the manufacturing floor, there's specifically for the electronics industry, we have what's called the Valor IoT equipment set, solution set. And what that does is a combination of software and hardware that does real-time data collection using our ODB++ standard. And we're able to use these collected data sets in order to obviously just do standard reporting and quality metrics and also process validation and verification. But that same data can be used to feed back into the model. And I described earlier we had the list of arrows, those chevron arrows, where we go through a process of developing a virtual simulation model and then doing data collection. Typically what's done there is, people walking around with a stopwatch and filling out an Excel file to do that. We would augment that. So in essence, pulling the data from a Valor solution in our case, or whatever system you may have, could be used to fill in that data set and be used as a basis by which you optimize the model, fine-tune the model, or use it to be the validation set for any model that you build for simulating an area.
Excellent. Thank you for that, Jay.
Okay.
Okay.
That answered that question.
Sounded good to me. Okay, let's see. We have one final question in the queue. Does the software come with a lot of the typical equipment and assets of a factory? That may make it easier to build the lines in a digital model.
Great question, and it's a pretty common question, actually. So the answer is yes. There's a starter library that comes with our virtual modeling software. The software itself has an object library of conveyors and equipment, various types of equipment, machines, and so on. And you can start out as generic as you want. I have a box here, and these are the input-outputs for the box, and these are the rates. And it's connected to this conveyor, and this is connected to this human type of thing, all the way down to modeling specifically a machine or a robot and how we can pull that data to model it more precisely. So the software itself comes with a starter library with a lot of the typical things you would want to see in a line or a building or a factory, and then you can fine-tune from then on, and then you have the model to use for any future simulation. It's a good question. I get it a lot, actually.
Excellent. Thanks, Jay. Looks like that was the last question. So I'd like to thank everybody for tuning in with us today and sticking with us throughout the duration of this event. Of course, I'd like to thank Jay and the whole Siemens team for that wonderful presentation. And to the audience, you will be receiving an email from us after the close of the event with a link to the on-demand session and also a link to download a copy of the slides. We'd like to thank you for joining us today. Have a wonderful day.